We start off by looking at subset selection. So subset selection deals with the case where I have a model with various predictors and I want to kind of figure out which predictors are useful and which should I include in my final model. We already know that if I look at the test error here, for example, as I keep on adding more and more predictors, I will be getting a better and better test error, but in principle I could also be adding irrelevant predictors, in which case I might be overfitting and this curve might be going up again. This is again the standard bias variance trade-off. In this case here, it seems like I'm not yet overfitting. The error keeps on going down and down as I add more predictors, and we again see this elbow structure. I add one predictor, I have this error here, I add another predictor, it goes down quite a lot. I have three predictors, it goes down quite a lot, but now actually adding more than three predictors, it seems to be only adding marginally to the error, so it's only reducing it so slightly. So again, by our rule of thumb, we will probably choose either the model with 3 or 4 predictors as our best model when we do the cross-validation and say, okay, this is the best model. Adding more predictors like 4, 5, 6, 7, 8 predictors, I don't really add much value, so I will choose the least flexible model. So how are those obtained? It says 1 predictors, 2 predictors, it doesn't say which ones. So actually the way how subset selection works, or best subset selection, is a very naive way. What it basically does, it starts off, let's just start off the model with 1 predictor. So we go through all possibilities. Try predictor 1, try predictor 2, try predictor 3, and look which of those predictors performs best. This will be the best model with 1 predictor. Now for 2 predictors, I will have to go through all possible combinations of 2 predictors, and I will then fit the model, look at the error and see which model performs best. This will give me the error for the model with 2 predictors, and so on and so forth. This will all be done on the training data, so I will see which 2 predictors work best on the training data, and then I will go to the test or validation set to obtain, say, this data point here. Obtain the one for 1, obtain the one for 2. Now for 3, I have to look at all possible subsets, including 3 predictors of my total set of predictors. And in generally, if I have p predictors here and I want to look at the subset using m of them, so m could be 2 or 3 in this case, I have p choose m as a combinatorial factor. So there are many possibilities of choosing it, and generally this number becomes very quickly very large. So if I had 100 predictors, it will be impossible to work myself through all the possibilities, and even worse, for each of the possibilities, for each of the subsections, I still have to fit a model, and fitting a model can be quick if it's linear regression, but it can be very, very slow if it's a more complex model. So this approach is very intuitive. Let me just go through all possibilities and figure out which one is the best one, but in practice it's not a very suitable approach to take. One which is better actually is a more greedy approach. So greedy in this case means like always kind of taking what is best right now and not worrying about kind of global optimality. You basically choose optimality locally. It means effectively you can do it in 2 ways, but for example I can start with no predictors at all. Now I want to add 1 predictor. So I just go through all the predictors, fit a model, and look which one of the predictors gave me the lowest error. This is my best model with 1 predictor, exactly as before. But now for 2 predictors, rather than looking at all possible subsets, I will now say, okay, now I already know the one which is the best predictor using 1. I will keep this fixed, and I will just ask the question, what is the best predictor to add as a second predictor? And now if there are p predictors in total, now we'll just have p minus 1 options, and then for the next one I have p minus 2 options. So it's not such a combinatorial difficult issue, because I only have to add one at a time. And this is what greedy means. I only do one up at a time there. You can see greedy approaches also in if you do route planning. So it's very difficult to plan the kind of globally best route, but I can always look locally what is the best direction to go next, and then hope that kind of this gives a good outcome overall. And often for those greedy approaches, you can show that the overall outcome will be good after all. So here you can see that actually, so if you compare to the previous one, here I have the black one, which was obtained using best subset selection. If I do a greedy approach, say backward or forward, I could start with no predictors and keep on adding one by one, or I can start with all predictors and keep on removing one by one. So if I do that, I will start here with all predictors. I look which one is the best one to remove. I go through all P of them, removing which one reproduces the lowest error, and I will go on, which one next to remove, and I will go on. And you see, I follow nearly the same path, but here for 3 is some differences. So it can be that maybe those predictors for 3 are not the same. You can imagine that, for example, if I keep on adding like one predictor, I add a second one. Now the model with 3 predictors might not include anymore the first one. This can very well happen, but this is where the greedy approach differs to the full subset selection. But the advantage of it is this is much faster, because effectively each time I only have to look at the kind of remaining predictors, rather than doing a full combinatorial exercise of looking at all the possible groupings of predictors of this number. So those approaches, backward and forward subset selection, are much better than best subset selection. So in practice, no one really does best subset selection. You do backward and forward subset selection, but even then we will see later that with techniques like regularization, we have a much better way of kind of tuning the parameters, choosing which parameters are best, than with the subset selection. The problem with regularization sometimes is that it doesn't really tell you which predictors I can totally discard. It might give us a lower weight, but some of the approaches don't totally discard them. But the technique we will talk about later, which is called lasso, actually helps us to totally discard some of the predictors, which effectively helps us to do some form of subset selection, but in a much better way. So I just wanted to briefly cover those 2 approaches, or 3 approaches, kind of best subset selection, backward and forward subset selection, because they have been relevant historically, and some people still use them, especially if the kind of statistical learning model is very simple. If it's very fast to do the fit, you can very well do this exercise. But once you go to more modern techniques of machine learning, where actually training the neural network takes 3 months, you can't do it so often. So you have to come up with a better way of doing this, and this is exactly what regularization does, and that's where we move on next.